In this problem, we have a pump which is discharging water at 20 degrees Celsius and at 57 meter cube per hour. So this is 57 meter cube per hour. It's meter cube, which is unit of volume. So this is actually volumetric flow rate, which is Q. We show it by Q. And then we also know that we can neglect losses, which means HF, friction losses are 0. The problem is asking about power, which is delivered to the water by this pump. So I select one point as point 1 before the pump and another point as point 2 after the pump. Pressure at point 1 is given, it's 120 kilopascal, and pressure at point 2 is 400 kilopascal. So as you can see, pressure at point 2 is larger than pressure at point 1, and the reason is that this pump is actually doing work on the fluid, so it causes an increase in the pressure of the fluid, of the flow actually. So pressure goes up from 120 to 400 kilopascal because of the work which is being done by this pump. We also have diameter of the pipe before the pump, which is 0.09 in meter, and the diameter after the pump, which is 0.03 in meter. So things that we know about this problem are pressure at point 1, which is 120 kilopascal, and we also know pressure at point 2, which is 400 kilopascal. We know diameter at point 1, which is equal to 0.09 meter, and we know diameter at point 2, which is equal to 0.03 meters. We also have the value of volumetric flow rate, which is 57 meter cube per hour, and we need to convert this to meter cube per second. So I need to multiply this by 1 hour over 3600 seconds. So this is equal to, this hour is cancelled by this one, and then Q is equal to 57 divided by 3600 meter cube per second. So this is volumetric flow rate. Step 1 of the solution is finding velocity of the flow before the pump, I mean velocity at point 1, V1, and velocity of the flow after the pump, which is V2, using the given volumetric flow rate. We know that from conservation of mass, Q1 is equal to Q2 is equal to that given volumetric flow rate, which is 57 divided by 3600 meter cube per second. So from here we can say V1 is equal to Q1 over area 1. This is equal to 57 divided by 3600 divided by area 1. We can calculate area 1 because we have diameter. So area 1 is equal to pi over 4 multiplied by diameter, which is 0.09 squared. And if you calculate that, you find out that V1 is approximately 2.49 meter per second. So this is velocity before the pump. And then I can calculate velocity after the pump by dividing Q2, which is equal to Q1, by area 2. And this is equal to, Q2 is 57 divided by 3600. And then we need to divide this by area 2. We can calculate area 2 because we have diameter. So this is pi over 4 times 0.03 squared. If you calculate this, you find V2 as 22.4 meter per second. So this is V2. So that's step 1. Step 2 is writing energy balance equation between points 1 and 2. Actually, the head form of energy balance equation, which is, is like this. It's like energy at point 1 plus head of the pump is equal to energy at point 2 plus head of the turbine plus friction losses. So we don't have a turbine here, so this term is 0. And the problem says we can neglect friction, so HF is also 0. So all we have is E1 plus HP, head of the pump, is equal to E2. The problem is asking about the power delivered by the pump to the fluid. So we are after this HP. So we need to have all the terms, all the 3 terms in E1 and all the 3 terms in E2, so we can find this HP. We know that this E1 is defined as pressure 1 over rho G plus alpha V1 squared over 2G plus Z1 plus HP. So the first 3 terms are E1. And this equals to E2. So we have similar terms like the first 3 terms on the left side, on the right side, but for point 2. So this equals to P2 over rho G plus alpha V2 squared over 2G plus Z2. So if we go back to the figure, you see Z at point 1 is almost equal to Z at point 2. The difference is just the radius of this pump, which is very small. So we can say Z at point 1 is almost equal to Z at point 2. So these 2 terms cancel each other, Z1 and Z2. And the reason is that Z2 is almost equal to Z1. So I can say HP, head created by the pump, is equal to P2 minus P1, P2 minus P1 over rho G. So I keep the term HP on the left side and I move this term P1 over rho G to the right side. And then the next term is alpha over 2G. And then we have V2 squared minus V1 squared. So from here I can calculate this HP. HP is equal to P2 minus P1. P2 is given 400 kilopascal minus P1, which is 120. And then we need to convert this to Pascal. So I multiply it by 1000. And then this is divided by rho G. Rho is density of water multiplied by G. So you can say density of water is 1000 multiplied by G, which is 9.8. So that's the first term. The second term is like this, alpha 1.06 multiplied by V2 squared minus V1 squared. V2, we found V2 here at the first step of the solution, step 1, as 22.4 and V1 as 2.49. So I have 22.4 squared minus 2.49 squared. And then that divided by 2G. So it's divided by 2 times 9.8. And then from here we can calculate this HP. So if you calculate this term, you will find HP as 53.9. meter. Now I need to convert head of the pump to power in terms of watt, or let's say kilowatt. So we know that power is m dot, which is mass flow rate, multiplied by G, multiplied by head of the pump. So this is equal to rho Q. This is the same as m dot. And then multiplied by G, which is 9.8, multiplied by HP, which is 53.9. And then rho Q is like, rho is 1000. So this is rho, this is density, times Q, which was given 57 divided by 3600. So if you calculate this, you will get 8.36 times 10 to the third watt, or you can say 8.36 kilowatts. So that's the power which is actually delivered to the flow by the pump. So the first step was finding velocities using the given Q. We found velocities because we knew we were going to use the conservation of energy, the head form of conservation of energy. And then when you go to the conservation of energy, you need V2 and V1. And that's why you calculate V2 and V1 using the given volumetric flow rate. So that was a step one. Step one was finding V1 and V2. And step two is actually writing this conservation of energy. This is actually a step two of the solution. You write the conservation of energy. In conservation of energy, we are after this HP. HT is 0, HF is also 0. So we write down the three terms of energy. And then you have all the values. You have P2, P1 are given, V2, V1. We found them in step one. We just substitute the values in here. We find HP, head of the pump, and then we convert head of the pump to power using this equation.